Okay, so any questions from previous material we've covered? Everyone's an expert on it so far, correct? If not, you will be hopefully before the test, right? Okay. All right, so we're going to continue on. We talked a little bit about energy production. I know we kind of blew through that pretty quickly, but this is going to be kind of where the meat of the topic is included here. So, the question is like, how do we produce energy within the body? How do we utilize it? And talking a lot about kind of the extracellular environment, kind of what goes into making up a lot of our fluids and different things like that. So, through this. All right, so looking at what's one of the most important sort of molecules that you carry within your blood that makes your body work? Any of them? Glucose. Glucose is very important. Absolutely, we need that for energy production. What else do we need that is also critically important? Perhaps yes, oxygen. There we go. Absolutely, oxygen is very, very important. If you don't carry oxygen, guess what? You die. Yes, absolutely. So you don't want to die. That's not good. Where do we carry our oxygen? On the hemoglobin, which is contained within the blood, right? So we're going to go down to kind of the breakdown. I know this seems simple, but again, we're trying to make sure everyone's on the same page so we can, hit the ground running for some of our other courses. But anywho, again, we're going to look at the plasma. We're going to look at kind of the breakdown of all these different these cellular spaces. Talk about the intracellular space, the extracellular space. But primarily, what we're going to focus on right now is going to be on cellular respiration and metabolism, right? Does that mean your cells individually are breathing? Not really. Like cellular respiration is really referring to using oxygen for energy production. And what do we use for energy? What's our currency of energy in the body? ATP, right? So again, we'll get into detail on how we actually produce that. So some of the common processes we're going to be talking about here are going to include things like glycolysis. This is going to be where we're actually breaking down sugar primarily into 2 molecules of pyruvic acid. It's going to be one of the first processes we're going to talk about here. We're going to talk about glycogenesis. Anyone know what that is? We kind of alluded to that already. We're generating glycogen, absolutely. Glycogen is good for what? Storage of energy, absolutely. Storage of glucose, so that way we can break it down later. What's the primary place that we store glycogen? Liver is a big place. We'll also see it in the muscles. We'll see it in other places as well. But the liver is going to be one of the primary storage of glycogen there, which is important. How about glycogenolysis? Break down glycogen right into some forms that we can utilize to produce new glucose during gluconeogenesis. And then how about lipogenesis? What is this? Generating lipids, generating fat, absolutely. Lipolysis, breaking down fats, yes, absolutely. When you need, say, glucose is not in abundant supply, if you need to break down fats for things, or you need to do things like produce steroids and other things like that, this is where lipolysis can be useful. And then ketogenesis we've mentioned before. What is that? Yeah, basically, if your body's in a state where it's going to be producing ketone bodies, we mentioned that happens in states of like starvation or in particular diets, low in carbohydrates. We'll get into more in detail why that occurs a little bit later on. But these are the primary things we're going to be talking about today, these processes, and going into more detail on those individually. So metabolism is going to be these reactions that are basically occurring within the body that usually require some degree of energy transfer to occur here. We mentioned that catabolism is what? Breakdown of products, and then anabolism. Building back up a product, absolutely. So you think about like anabolic steroids. What do you think happens when you take an anabolic steroid? Yeah, you're building muscle, you bulk up, right? So that's why I think anabolism is what I think anabolic, catabolism, catabolic. You'll see there's other types of steroids that are actually very catabolic and actually break down the body in general. But anyway, this is kind of the 2 main processes that are occurring here that kind of make up metabolism. All right, so with our catabolism, we're going to find that we're going to be breaking down precursor molecules in order to produce ATP, right? So we mentioned that adenosine triphosphate is going to be our primary energy currency. We're going to be utilizing this for all sorts of different processes, and we're going to see this is coming. Basically, we're getting these ATP generated from our macronutrients. We mentioned macronutrients are what? Carbs, carbohydrates, fats, and proteins, right? So those are your 3 main macronutrients that are utilized for energy production. And again, we'll find that some of them are going to be preferred in some states versus others. That's okay, but they're going to be eventually oxidized into developing ATP, and then we can use that for all sorts of things. We can use it for things like active ion transport. We're going to talk about that a little bit later on. We can use it for things like muscular contraction, very important for that. Synthesis of new molecules, that anabolism there, and then cell division and growth, which we kind of already covered already. Notice here, if you remember, we talked about calories and how actually when we talk about calories, like on a food label, you're actually talking about kilocalories. But looking at this on a molar basis, you can see here that's actually pretty high energy sort of thing. So a mole of ATP contains roughly 12 kilocalories, or 12 calories that we were kind of used to thinking about like on a food label sort of thing. And again, where does ATP actually get produced primarily? In the mitochondria, right? And that's located within the actual cell itself. So you can see on this picture here, we're using glucose, fatty acids, amino acids. All of these are going to be broken down to eventually generating some ATP. We're going to look at the different steps that go into that, but the mitochondria is super important here. And notice this is going to be utilizing oxygen, right? We absolutely have to have oxygen here. And what type of metabolism do you call this? Aerobic metabolism, right? So we're going to call this aerobic respiration that's occurring here. Our metabolism is that's happening within the mitochondria. What do you call it when you have no oxygen around? Anaerobic, absolutely good. So anaerobic metabolism is also going to be a thing that occurs because, again, you can't always deliver adequate amounts of oxygen to the body. Sometimes you're going to be in a state where you cannot do that to the tissues, and so you have to switch over and kind of use some reserve methods. They're going to notice that's going to be pretty inefficient means of generating energy, but sometimes you got to do what you got to do to get that ATP produced, right? You're going to see the main byproducts here of aerobic metabolism is going to be carbon dioxide and water, okay? So again, all that glucose, all those fatty acids or amino acids eventually will get broken down into carbon dioxide and water, and that carbon dioxide we then will eliminate through the lungs primarily, and that water we can utilize for whatever else we need to, right? Okay. So and we're going to talk about glucose first, because again, that's going to be one of the quickest ways that we can develop ATP. One of the more energy efficient ways we can utilize glucose. This is going to be occurring in 3 steps. First off is going to be glycolysis. This is actually happening within the cytoplasm itself. This is outside of the mitochondria. This is going to be an anaerobic process, right? So this does not require any oxygen for glycolysis to occur. After that, it's going to enter into the Krebs cycle. Anyone know a different name for the Krebs cycle? Yeah, citric acid cycle. So again, I see some like PTSD flashbacks for some of you guys. Think, oh gosh. We're going to talk about it briefly. We're not going to go into super big detail. Again, the big thing I want you guys to know is like kind of what are we putting into the system and what are we getting out of the system. Those are the main things I want you guys to know. I'm not going to have you know it goes from citric acid to this. I don't care about that, right? Not important for our purposes. But once you get through the Krebs cycle, and then this is occurring within the mitochondria, this is an aerobic process. So again, if you don't have any oxygen, this is not going to occur, right? Glycolysis, though, is going to be oxygen independent. In this case, after they go through the Krebs cycle, electron transport chains are going to occur here. This is actually within the mitochondria as well. And again, this is an energy or oxygen dependent sort of process. This is aerobic. This is where we're going to get the bulk of our ATP actually being formed here. And we'll go through those details in just a minute. Everyone with me so far? Fantastic. Okay, so again, looking at energy metabolism, primarily where are we getting glucose from? Carbohydrates, but where do we get those from? Food, right? So our digestive tract will be a major source of glucose kind of coming in. Hopefully everyone had a really good breakfast, otherwise maybe your glucose levels are doing a little low. So if I see some of you falling asleep, I'll assume that's what it is, right? Otherwise, where can you get it from? The liver is going to be another big place where you're going to get a lot of your glucose from, right? And so again, once that is, again, this is going to be that process of gluconeogenesis that's occurring within the liver that will release glucose into the bloodstream, or you take it into the GI tract, and then it can float around in the plasma, right? It'll eventually get into the cells here. You guys remember what hormone helps get glucose into the cells? Yeah, we'll talk about insulin in the endocrine section later, but insulin is going to be really important for that process. But in terms of energy production, you're going to notice that the glucose is going to undergo glycolysis, right? We're going to generate pyruvic acid, and again, it's good to know what the inputs are, what the outputs are. So again, putting in glucose into glycolysis, we're getting pyruvic acid molecules out of that, and we'll show some more details here in a second. At this point, you can go down two pathways, right? We're going to find there's an anaerobic pathway and there's an aerobic pathway. So what are some situations you might think we would go into an anaerobic pathway? Yeah, good during exercise, right? So again, when you think of exercise, you think of like aerobic exercise, which is, cardio, things like that. But there's also anaerobic exercise. What are some examples of that? I was thinking like weightlifting, right? You think like weightlifting as being like a kind of sort of anaerobic sort of exercise, right? Because again, you can deplete your oxygen stores pretty quickly, and then once you're depriving the tissues of that oxygen, then especially the muscles, they're going to switch off and go over to the anaerobic pathway. That is one instance. So exercise is a good answer. What else? What if, say, you were like suffocating, where there's some reason why you were not actually intaking oxygen, right? So that could be one way. Say, for instance, you have a patient who has a syncopal episode and they have respiratory depression, not breathing. Guess what? You're going to switch over to an anaerobic sort of pathway, right? So again, when you think about people who are not breathing, what do you think their pH does typically? They typically decrease. They get more acidotic, right? So again, when someone stops breathing and become acidotic, their pH starts to drop. That makes sense because, one, we're holding on to a lot of CO2 in the blood, we're also holding on to a lot of lactic acid because, again, they don't have oxygen to produce ATP. They're switching over to this anaerobic pathway, right? So if you have someone who is not breathing well, chances are their lactic acid is going to be increased, right? Because they can't actually utilize that oxygen in the tissue. Some other things like cyanide poisoning is another thing where you can actually find that that it actually shuts down the mitochondria, and that will shunt that process over to producing lactic acid. So those patients get very acidotic, and they're not making a lot of ATP very efficiently. So anyway, lots of reasons why you may go this anaerobic pathway. Primarily, though, we'd like to stay within the aerobic pathway and utilize mitochondria to go through the citric acid cycle or the Krebs cycle, and then we'll undergo electron transport chain to hopefully produce a lot of ATP and then some carbon dioxide and water, right? Carbon dioxide then can get out of the cell, we'll breathe it off, and then you're good to go, okay? So during glycolysis, note that we're putting in 1 molecule of glucose. Anyone know how many carbons are in glucose? 6, yeah, so remember C6H12O6, right? So again, we're going to put in a molecule of glucose, that's 6 carbon chain, and that's going to get broken down into 2 molecules of pyruvic acid. Okay, so again, do I want you to memorize every step of this process here? No, the answer is no. You can be a little bit relieved that no, that is not the correct answer, right? So again, but what I do want you to know is that this kind of what the outputs are going to be from the system here. So what you notice here is I'm putting in glucose. What's one of the first things I'm utilizing here? ATP. So right, well, wait a second, I'm trying to like generate energy. Why am I utilizing energy here? Well, just like, you know, the guy that tried to sell me on that, you know, multi-level marketing scheme, sometimes it takes money to make money, right? May have run off with all my savings, but don't worry about that. That's not the point. Main thing here is you're utilizing a little bit of ATP, namely 2 molecules, and then this is going to generate, eventually going to generate our pyruvic acid. Notice here that we're actually also generating a few ATP molecules as well, right? So again, we're going to be putting a few molecules into the system. We're also going to be getting some out of it. So we're actually going to have a net increase in amount of ATP available to us. The other big thing to notice here is we're going to be generating these hydrogen ions, okay? Hydrogen ions are going to be very good because these are going to participate in the electron transport chain. We can utilize these later in the mitochondria in order to help produce new ATP. So just kind of keep those in the back of your mind. Just know that in this case, this net reaction, we're putting in a molecule of glucose, putting in some ADP, some phosphate here, and then we're going to be generating 2 molecules of pyruvic acid. Right, so then this, once it breaks off in 2 molecules, and you can see it's going to be kind of everything will be kind of doubled as we go forward here. We'll produce 2 ATP, and this is a net increase of 2 ATP, right? Because we utilize 2, we produce 4, so that means our net is going to be 2, and we have now 4 hydrogen ions. You know, we're going to see this again because we're going to have some repetition here. We'll see. So again, looking at the net energy gain here, it's going to require some amount of energy to activate this process here. So we're going to invest, say, 2 molecules of ATP. Hopefully, in the long run, we're going to kind of get more bang out of our buck for that. So again, investing 2 molecules now is going to get us a whole lot more later on, as we'll see. So we're going to get a net gain of 2, even though the total product is actually 4. So we invested 2. We're getting 4 out, so the net increase is going to be 2 here, right? And now we have 2 molecules of pyruvic acid. That means we can now kick off 2 citric acid cycles, as we'll see here in a second. Okay. And notice here, this NAD, this is going to be one of these cofactors. Usually NAD, and we'll also see the FAD, are going to be carriers of electron, or carriers of hydrogen ions here. So you see that in these processes, we're having 2 NADs convert over to NADH. So that oftentimes you're going to find these carriers that are holding onto those hydrogen molecules. And again, these can be utilized later on to help produce new ATP later. Right? So again, this is going to be a pretty efficient process, as we'll see later on. Everyone with me so far? Fantastic. Okay, again, just another kind of pictorial example here. Again, we're putting our glucose in. We're kind of increasing the total free energy of the reaction by putting in 2 molecules of ATP, because again, these are high energy molecules. And then we're going to have drops here because we're actually picking up 2 hydrogen ions here in the form of NADH. We're generating 2 ATP here and 2 ATP here. So now we have 2 molecules of pyruvic acid. We have 4 hydrogen ions that have been produced, and a net of 2 increase in our ATP count. Okay. All right. Just another picture kind of showing you the exact same thing. And notice each one of these pyruvic acids we've produced can now go into the citric acid cycle themselves, right, after they get converted into another product we'll see here in a second. But just know that this is going to have this nice effect of kind of doubling what we're able to generate here. Okay, the next step of the path, and we'll kind of talk about the anaerobic pathway right now. So again, we've undergone glycolysis. We mentioned that glycolysis is aerobic or anaerobic? Yeah, right now it's still anaerobic, right? We've not generated, or we've not utilized any oxygen in this process here. Let's look at what happens if we didn't have any oxygen available. Let's look at what would happen if we had to undergo the anaerobic pathway. Say, for instance, we're really in a strenuous physical exercise. We're running a marathon. We're starving our tissues of some degree of oxygen. We're going to switch over to generate some lactic acid, as we'll see here. So this anaerobic pathway, or this lactic acid pathway, notice here is going to require no oxygen to complete the breakdown of glucose. Because again, once you generate the pyruvic acid, you don't want to build up with that. You want to do something with it, because otherwise it's going to inhibit that process of breaking down glucose, essentially. So this pyruvic acid is going to undergo reaction with the enzyme lactic acid dehydrogenase in order to form lactic acid, right? So again, when your muscles get sore, that's usually due to the buildup of things like lactic acid or other reasons, but that's one of the big things you'll see there. And this lactic acid, because it's not a very energy efficient process we're going to see here, but what it does is allow for continued glycolysis. We can continue to break down more glucose into pyruvic acid, and we're going to see that this is not going to be kind of a terminal pathway here. We're going to see that we can actually utilize this lactic acid later on, but primarily the liver is going to be one of the big places that actually handles that lactic acid. Okay, so this is a reversible process. Once you get to a point where you can have oxygen being delivered to the tissues again, you're going to see that this is reversible. Okay, so that's a big thing to note there. Okay, so on the flip side, and we'll see what happens to lactic acid a little bit later on, so just kind of keep that in the back of your mind, but lactic acid dehydrogenase is the enzyme that works on that there. Okay, so switching back over to the aerobic pathway that utilizes, we're going to see here that we're going to have this aerobic respiration, this aerobic pathway. We're going to have the pyruvic acid. It will go from the cytoplasm into the mitochondria, and then here's where it gets used in the Krebs cycle. The pyruvic acid itself doesn't get utilized. It's going to get converted into something else, as we'll see. Anyone know what it gets turned into? Good. I didn't know either when I was having to re-review all this stuff. Again, the details here are not going to be what's really the important thing. Just know what the inputs and the outputs are really going to be. So again, pyruvic acid is going to be coming in here. You notice it's actually going to remove some carbon dioxide, so it gets converted into acetic acid. Acetic acid can then combine with coenzyme A, and now we're going to develop acetyl-CoA. Okay, so this is the primary thing that's going to be entering into the citric acid cycle to kick that off. Okay, so pyruvic acid turns into acetyl-CoA, and then we can utilize that for the Krebs cycle. Right? Notice this is just an intermediary sort of step here. There's no ATP that's really being formed here. However, a few of the hydrogen ions actually get liberated here are going to be later utilized for ATP. So again, we'll kind of keep our running tally of energy production later on. So I'll have kind of a final slide that kind of shows us everything we've kind of produced at the very end of this process. But just know that some of these hydrogen ions can be utilized to produce ATP later. Notice this is happening within the mitochondria. So we move from the cytoplasm into the mitochondria now. Okay, another picture kind of showing the reaction that's happening here. So pyruvic acid plus coenzyme A, eventually turn it into acetyl-CoA. You've produced some carbon dioxide, which is then going to be eliminated as waste products, and then the 4 hydrogen ions can be utilized for ATP production and during the electron transport chain later on. All right, so now everyone's favorite, the Krebs cycle. I remember we had to come up with like just really inane sort of ways to remember this. I remember we had to like little stories that we would tell about a Kentuckian doing something. I don't remember. We had one study buddy who was really good at like making anagrams and things like that, but don't memorize all that. Main point to know is that we're going to be entering in acetyl-CoA. This is going to get converted over into citric acid, and this is going to be kind of the first step of the process here. And notice here we're generating things like carbon dioxide, but we're also going to be generating a decent amount of hydrogen ions. That's the other big step that's happening here. So acetyl-CoA gets transformed into citric acid, and that's going to kick it off. So what's happening here, we're going to notice that during the Krebs cycle, again, this is just with one molecule of pyruvic acid. And remember, when we break down glucose, how many of those do we get? We get 2. So remember, this is happening in tandem with this another pyruvic acid molecule that's undergoing the Krebs cycle here. So again, we're forming one molecule of ATP for every molecule of pyruvic acid. We're also generating 3 molecules of NADH plus 3 additional hydrogen ions. So it's kind of 6 hydrogen ions now we have to work with. And then we're also going to generate 1 molecule of FADH2. So notice that's carrying 2 hydrogen ions that we can utilize for ATP production. And we're also generating some CO2. CO2, again, is just a waste product. We can get rid of that later on, right? So again, notice here, we're not generating a ton of ATP. This is not the major step of this occurs, but we are generating a lot of hydrogen ions, and that's going to be good because the electron transport chain is going to require those to make most of our ATP. So that picture kind of showing the same thing, glycolysis. Again, we're breaking down into pyruvic acid. This is going to generate acetyl-CoA, and that's going to end up additionally forming a little bit of ATP, but mostly a lot of hydrogen ions and some carbon dioxide. Okay. And again, if you wanted to draw out all the chemical structures, as I had to one time, you don't want to do that. Don't worry about it. Just know this is just another way to look at it. But again, the products here are what's important that we're actually developing here, right, at the end of this process. Okay, So looking at the final products of the Krebs cycle, kind of where are we at right now in the process? So we've undergone glycolysis, we've undergone the Krebs cycle. Where are we at? So we've broken down 1 molecule of glucose into 2 molecules of pyruvic acid. Now at this point, what we've developed overall is going to be 6 molecules of NADH plus 6 additional hydrogen ions. We developed 2 molecules of FADH2, and we developed 2 molecules of ATP and 4 molecules of carbon dioxide. Okay, this is where we're at. So again, notice all these nice electrons, all these nice hydrogen ions here. We're going to be utilizing these to make ATP in just a moment. Okay, so again, additionally, by including the products of glycolysis here, note that we have 4 ATP that have been formed in total, and we have 24 hydrogen ions. All right, so that 1 molecule of glucose is now produced at this point 4 ATP and 24 hydrogen ions. All right, so now what's going to happen? Electron transport chain, right? This is where the actual, this is where we're going to get all of our return on our investment. This is where we're going to get our big payout that never came from me and my pyramid scheme, right? Anywho, so again, 90% of this ATP formation actually occurs during this step here, during oxidative phosphorylation. There's a really important process here. This actually is clinically really important for me as a toxicologist because there's certain things that can actually uncouple this process here. So you can generate, ATP, or you can generate acetyl-CoA, you can go through the Krebs cycle, but if you can't do this oxidative phosphorylation, you can't really produce a lot of ATP, and this is a bad thing to interrupt. So if you ever hear of like an aspirin overdose or cyanide overdose, this directly inhibits this process here. So this is vitally important to make sure you have a good, healthy human being that's producing a lot of ATP. Anyway, so what happens here is the hydrogen atoms, again, getting split into their electrons in the hydrogen ion. This is then going to form water. At some point, we're going to have some more water. It's going to be an output of this system. And then each of the 2 electrons that pass through, we're going to generate 3 ATP. 2 electrons are going to end up generating 3 ATP each. And so, by putting in 20 hydrogen ions here, they're going to end up eventually making 30 molecules of ATP. We're then going to have an additional 4 hydrogen atoms are going to make 4 ATP. So then our total here we're going to see, because remember with glycolysis, and during the citric acid cycle, we had 4 molecules of ATP that were formed during that process there. Now we're including an additional 34, right? So now 1 glucose molecule has a maximum attainable amount of ATP of 38 molecules. So really, this is really one of the key takeaways here, is that for every glucose molecule, we're getting 38 ATP, right? Now, is this 100% efficient? No, remember, none of our enzymatic processes are 100% efficient. Notice that we are going to be generating waste products. So we mentioned things like carbon dioxide, water. What's another big waste product we have during these reactions? Heat, right? Again, that's why we get hot. So if you're in a state where you're in a hypermetabolic state, people tend to get hot, and this is because of that, because you're generating a lot of heat as a waste product of a lot of these reactions here, right? So you don't have to remember any of these different enzymes that are here. Just know that there's different enzymatic processes that are processing those electrons and eventually generating that ATP. And just know that eventually what we're going to be generating, and again, a lot of see how the NADH is donating those hydrogen ions, that's where we're getting a lot of those electrons generated there. But anyway, so again, we're getting a total molecule count of ATP, 38 from 1 molecule of glucose, right? Okay, any questions on that? So again, know what we're inputting into each of those steps, know what we're getting out of each of those steps, and kind of what the total kind of count is going to be at the very end, right? Simplified version of that. Again, you don't have to know each of those steps of what citric acid gets converted to, all that. You don't need to know that. Just know the basics there. Okay, so what else happens here? So let's say we have, too much glucose around in the blood. Let's say we don't need all that glucose floating around. We don't need that for energy production. How are we going to store it? Glycogen. We're going to undergo glycogenesis, right? We're going to generate new glycogen. It's going to help store that. And we mentioned one of the big places we store glycogen is the liver, right? Other places? Muscle is going to be the other big place where we're going to store a lot of glycogen, right? And again, these are our energy reserves essentially. So mentioned cardiac muscles can also store some of this, but you'll find a lot of this in the liver and then the skeletal muscles. The important thing to note here is that the glycogen stored in the skeletal muscles and the cardiac muscles are not going to be for kind of general consumption throughout the rest of the body, right? So again, they're reserving it for themselves because they need that to continue producing energy. However, the liver is going to be a little bit more of a charitable sort of organ that's going to say, hey, you need some glucose, let me break it down and undergo gluconeogenesis. Let me deliver that to the rest of the tissues, right? Let me deliver that to the blood. They can go around everywhere else. One important distinction there with glycogen. So when other cells in the body are going to need glucose, that's when you're going to have hydrolysis of glycogen, and it's going to occur within the liver. Remember any hormones that might affect this? Cortisol. Cortisol? Yeah, cortisol might be one that can do it. What's another one we talked about in relation to things like blood sugar management? Glucagon, absolutely, yeah. So again, if you get into a state where, I need increased blood sugar, well, I got to produce that from somewhere, and glycogen is going to be one of the big places. Glucagon is a major hormone that helps to stimulate this process here. So glycogenolysis is where we're going to be breaking down glycogen and producing gluconeogenesis, right? We're going to be producing new glucose to be released into the bloodstream, and the liver is the primary place where you see this occurring. Liver is the only place where we're yielding free glucose that gets secreted into the blood. Essentially, what you find in the skeletal muscle and other muscle tissues is that they tend to hold on to a phosphorylated glucose form that can't enter the bloodstream. However, you don't have to worry about that with the liver because they have an enzyme called glucose 6-phosphate. They'll actually end up removing that and allow the glucose to get back into the blood. So that's why the liver is able to share it with the rest of the body. The muscles can't really. Okay, and so some other things that can affect that, as you mentioned, cortisol is one thing that can actually increase gluconeogenesis and things like that. But also think about like your stress responses. Think about your fight or flight sort of responses. Glucagon is going to be a big one that helps to increase glycogenolysis and gluconeogenesis, particularly if you're in a low blood sugar sort of state. But also think about, if I'm in a fight or flight state, say alligator popped out at me, I need to run away. I need energy to be produced, right? I need glucose. And so things like epinephrine, which can be released by the adrenal glands, can be one of those things that gets released in order to help influence that, right? So again, we'll talk about different receptors that cause that to occur, but just know that can be one of the kind of stimulatory things that causes the liver to now produce new glucose. Okay, so again, that glycogen gets converted to glucose within the muscle, but it does not enter the bloodstream, but in the liver it is going to be able to be delivered there, and that's due to that having that glucose 6-phosphatase. Phosphatase would just be removing one of those phosphates, and so that allows it to get back into the bloodstream. Okay, so the question also comes up is like, well, say we were in a highly strenuous state, we were producing a lot of lactic acid due to our muscles being in an anaerobic state. We utilize all the oxygen in the muscles. We end up having to undergo anaerobic metabolism, and we end up generating lactic acid. What happens to that lactic acid? I mentioned that we can undergo a reversal sort of process that occurs, and that's going to be happening within the liver. And this is what we call the Cori cycle that's occurring here, right? So again, during exercise or strenuous activity, producing lactic acid, that lactic acid can be released into the bloodstream. You can actually measure that. Something you can measure in a lot of patients you suspect to be septic, or if they have acidotic, things like that, you would measure their lactate level to see kind of what their level is if it's higher than normal. But that lactic acid can be delivered over to the liver. The liver is going to have an enzyme called lactic acid dehydrogenase. It's going to convert it back over into pyruvic acid and then also generate some hydrogen ions there as well, right? So notice here, this is not going to be a completely energy efficient sort of step here. It's not preferable to undergo the Cori cycle. However, this is one way we can kind of scavenge that lactic acid to get that pyruvic acid. Because what can the pyruvic acid do for us? You can eventually produce energy, right? You can undergo the Krebs cycle, you can eventually undergo electron transport chain. We'll see there's some other steps that can happen here as well. So looking at this picture here, we have our muscle cell on the left, we have our liver cell on the right. What's another name for a liver cell? Yeah, hepatocyte, good. So we're going to have, say, for instance, glycogen being stored in the muscle that can get broken down into glucose eventually, right? So we're producing glucose, and then pyruvic acid can be formed there. So say we're undergoing strenuous exercise, that pyruvic acid is going to undergo anaerobic metabolism over to lactic acid, and so then that can be released into the bloodstream, right? Once that goes into the bloodstream, that can then be converted back to pyruvic acid within the liver, and then it can either be stored as glycogen eventually, or it can actually be changed back into glucose, the gluconeogenesis process there, and then can release that glucose back into the bloodstream, where it can eventually go back to the muscles. So notice here, it's not the most efficient way to do things. However, it is one way we can help to utilize that lactic acid for better purposes later on. Make sense? So again, just another picture kind of showing you kind of the same thing happening here. The glucose can, it doesn't have to go back to the muscle, it can really go anywhere once it's released back into the bloodstream. But note that this is an ATP dependent process. So overall, you end up losing a net amount of 4 molecules of ATP. So because of that, this cannot be done indefinitely, right? Because we're kind of decreasing the efficiency here, there's going to be a limit to how much we can do this. Usually, you're going to find that's why you just can't keep utilizing the muscles in an anaerobic state forever. Eventually, they tire out, right? And then that's mainly because we can't, we don't have a good way to produce ATP in a very efficient sort of manner there, right? So again, also this is going to be pushing that lactic acid burden back onto the liver, where it can more efficiently kind of convert that back, versus the muscles don't really have a good ability to do that necessarily. Just another picture kind of showing the same thing here. Again, glycogen in the muscles during exercise is going to be converting this over to pyruvic acid. That will then produce lactic acid. If you have inefficient amount or an inadequate amount of oxygen around, that goes back to the blood. Lactic acid gets converted back to glucose eventually, right? Or it can be stored as glycogen or whatever. It just depends on what the body needs at that moment, right? So what about our other macronutrients? That's basically how we can manage glucose, or how glucose is managed to produce ATP. We also know that things like fatty acids, we know that things like amino acids can also be used for energy as well. And again, this is what we're trying to harness when we're doing things like ketogenic diets and starvation states, or states where you're not able to get enough carbohydrates and glucose. So what we're going to see is that they will eventually undergo similar enzymatic processes, but there's going to be a few other starter steps they have to go through before they turn into pyruvic acid, essentially, right? So we're going to see here that proteins eventually get broken down into amino acids. They can be turned into acetyl-CoA. We're going to see the polysaccharides, which are what? Yeah, just long chain sugars, right? So again, they're going to have multiple sugars attached together. They can be broken down to monosaccharides. We've already covered this in the beginning part of this lecture. And then fats can be broken down to glycerol and fatty acids. Remember how we were looking at those fatty acids, how they had the glycerol molecule followed by the three, or I'm sorry, when looking at triglyceride, had the glycerol molecule and 3 fatty acids attached to it. We're going to see that's going to come into play here in just a minute. But those can be converted to acetyl-CoA too. Once it gets turned into acetyl-CoA, it can go undergo the Krebs cycle and the electron transport chain, right? All right. So just looking at this, we already looked at the glucose pathway here and how we can generate ATP from this, or generate pyruvic acid and acetyl-CoA. Looking at the fats here, we can also see that as they get broken down, these triglycerides, that's going to be one of the main things you can measure in the blood as a measure of your serum lipids. But you'll release those triglycerides, which we said had that glycerol molecule that was attached to 3 fatty acids. That glycerol can then be utilized to potentially produce pyruvic acid, or you can actually utilize the fatty acids themselves. You can break those down into shorter chains of carbon that can be broken down into acetyl-CoA, right? And again, we mentioned that it's like a gram of fat has roughly how many calories to it? Yeah, 9 calories versus a gram of carbohydrates has roughly what? 4 calories, right? And again, when we have a nutrition section later on, we'll talk about that. But just know that fat generally has a lot more kind of energy to it because it has these long carbon chains that you can generate into acetyl-CoA. Now the question is, can they be used as quickly? No, you're going to find that glucose is going to be the fastest way we can get energy produced. However, it can still be utilized if you're in a pinch, or if you're in a starvation state or dieting or something like that. You can utilize those fatty acids and those triglycerides to produce energy as an alternative fuel source. Okay, so again, looking at lipogenesis, this is going to be the process where we have, say, too much glucose floating around, we have too much, and we need to store some of this energy for later use. So again, some of this can be stored as glycogen. We'll also find that we can convert some of this over into fat eventually, right? So again, when glucose doesn't complete glycolysis, say we have too much glucose around, say I just had a big bowl of ice cream or something with a lot of sugar in it, I don't need all of that sugar. It needs to get stored somewhere, right? And so you're going to find that these fatty acids can combine with glycerol. That's going to form our triglycerides. Once you form these can eventually be stored within either the adipose tissue or also the liver as well. So again, these are different places you can store these for later use, right? So that's lipogenesis. The flip side of that's going to be lipolysis, right? We can break that down for energy production later on, right? So again, we have 3 fatty acids combined with the glycerol molecule. That's going to be forming that triglyceride, right? Okay, so when we need energy, lipolysis can occur here, and that's going to be basically hydrolyzing those triglycerides. So we mentioned the glycerol can be utilized for to eventually turn into acetyl-CoA. The fatty acids themselves can be broken down to eventually form acetyl-CoA as well. And we're also going to talk about ketone production here in a minute. But again, primarily you're going to find that a lot of the fatty acids and triglycerides are stored within the adipose tissue. And then the enzyme lipase is going to be really important for this, not only in helping to digest fats in the GI tract, but also in kicking off this lipolysis pathway. So if say you're in a starvation state where you're not intaking a lot of glucose, your body needs alternative fuel sources. It can go to the fat cells and say, hey, let's increase the activity of lipase, break down these triglycerides into, so they can float around the bloodstream. They can be broken down into their constituent components, glycerol and fatty acids, and then we can use that for energy production as an alternative source, right? So again, that's why you see people who are going to ketogenic diet, they typically drop fat pretty quick because they have not a lot of glucose around, and so they need that alternative fuel source. Okay, so again, lipolysis, again, we're breaking down the triglycerides into fatty acids and glycerol via the enzyme lipase. The fatty acids themselves can enter the bloodstream. They can be used directly for energy, usually breaking down some of those carbon chains into some constituent components and turned into acetyl-CoA. The glycerol tends to prefer to go to the liver, where it can be used to generate new glucose, right? Usually through that process of gluconeogenesis. So again, fatty acids are a little bit faster to be utilized for energy production. The glycerol tends to go to the liver, where it can be turned into glucose for later on, right? So one picture showing this, here's the adipose tissue, here's the blood, here's the muscle here, and then here's the liver. So imagine we have the adipose tissue breaking down triglycerides, you have our fatty acids, these can be transported over into the muscle, and you can actually utilize those fatty acids, and we're going to undergo a process called beta oxidation. This is where a lot of our ketone bodies are going to be produced here, but also you're going to generate acetyl-CoA. And again, we mentioned that that's going to be good because that can undergo the Krebs cycle and produce energy. Looking at the adipocyte versus the liver, you can see that the triglycerides get broken down into glycerol and the fatty acids. That glycerol can go into the liver, undergo a process to actually produce new glucose. Right. So again, everything gets utilized from the triglyceride there. Any questions so far? Anyone with me? That's early. But again, that's why we record things, so you can go back and look at it later if you need to, so it's okay. Anyway, so looking at ketone body production, when the rate of lipolysis tends to exceed that rate of fatty acid utilization, so say for instance I'm starving, or say for instance I'm dieting, or in the case of say like a diabetic patient who has a lack of insulin, the insulin to transport a lot of these things like glucose into the cells, you undergo this ketone production, right? And so basically we're going to have too many fatty acids around. The liver cells are going to try to convert those over into a usable form, but the fatty acids will be broken down to acetyl-CoA, and then kind of an additional byproduct you're going to see here is going to be the formation of these ketone bodies, right? And so when you have a large amount of buildup of ketones in the body, we call that ketosis, right? And so you have things like beta-hydroxy butyric acid form here, also acetone. Remember, because if you ever look at someone who's in DKA or like diabetic ketoacidosis, their breath is usually described as what? Kind of fruity, right? And a lot of it goes back to these ketones are actually being produced here, right? So again, if you have too much buildup of fatty acids within the blood, you undergo this process where they're going to be generating ketone bodies, right? And you can actually measure that. Anyone know how you measure ketone production? Yeah, usually in the urine, so they'll have like little urine dipsticks that can actually measure. Because again, those ketones, if they're not getting used up, they're not being utilized for any kind of energy processes, they get eliminated within the kidneys, right? And so they'll just go out in the urine. You can actually measure that in with the dipstick and determine if your patient is in ketosis or not. That's one of the things they'll see, like a keto diet, they'll be checking their urine to see if they're actually in ketosis or not. Okay, proteins can also be utilized for energy production. Again, this is not preferred because we like proteins to do what? Them for enzymes, we like them for muscles, we like them all sorts of things. But in a pinch, they can also be utilized for energy production as well, right? Amino acids, when they come into the body, they're typically utilized with their nitrogen. Nitrogen there, we call it the nitrogen pool that we'll be contributing to. So if you eat like a big hamburger or something, you're kind of contributing to that nitrogen pool, those amino acids. Now, we mentioned that some of these are going to be essential amino acids, some of these are non-essential. Essential just means that our body cannot produce them on their own. I'll show you a list of these in a second. However, the non-essential ones, we can actually produce. We can actually cause some conversions to happen within the body via enzymes and produce some of these non-essential amino acids. And again, I'm not going to have you memorize this list. I'm not going to ask you specifically, hey, is lysine an essential or non-essential amino acid? You can look this stuff if you really need to. I can't tell you how many times clinically this has ever really come up. Maybe once, and that's going to be regarding, we kind of mentioned, but we mentioned enteral nutrition being things you're taking in orally, but there's also parenteral nutrition I mentioned, which is that total parenteral nutrition where you're going to be giving food via the IV, right? You're giving all your macronutrients. I deal with this every day. So for instance, when I was back at Nemours yesterday, we had like 6 or 7 kids on TPNs. You have to make sure they're getting all their macronutrients and micronutrients. And one of the things you have to make sure is they have to get all their essential amino acids. Because again, these are kids who are in PO, which means what? Nothing by mouth, so they can't eat anything. So we have to give them all their nutrition through the IV, and we have to make sure they get all their essential amino acids. So they have specific formulations of proteins we're giving them that has all of these in there. And notice here, like some of these are going to be essential in children, but not in others, right? So for instance, histidine, you have to make sure to use a pediatric specific formulation to make sure they get their histidine. Otherwise, if you run into deficiencies of these, you might not be able to produce your non-essential amino acids. Okay, so just give you an idea of kind of where this might come up clinically. Make sure you're using the appropriate things to take care of your patients, because otherwise, if you don't give them this, they're going to run out eventually, right? Okay, so one of these processes we can help to kind of convert some of these amino acids includes transamination. Again, this requires B6 as a coenzyme. Remember, coenzymes are just going to be requiring other molecules to kind of help to kick off that enzymatic process. But one of the big ones you're going to see, and you'll measure quite frequently in your patients, especially if you're considering they might have like hepatic damage, is going to be the liver enzyme ALT and AST. They stand for alanine aminotransferase and aspartate aminotransferase, respectively. These are enzymes that are important for converting some of these amino acids into other forms. So, for instance, we can convert glutamic acid into alanine, and we can convert things like glutamic acid into aspartic acid. And when you measure someone who's having liver damage, usually you'll measure that the blood is, or as the liver gets damaged, it'll release these enzymes into the blood, and you can measure that. So if I have someone who has liver damage, I'll know they'll have really high AST and ALTs, and I know that's indicative of some sort of liver dysfunction. However, these amino acids can also be utilized to actually produce pyruvate. And we know the pyruvate gets converted into acetyl-CoA, and that can be utilized for ATP production. Again, this is more going to be in a starvation sort of state. You know, when your body's in more of a catabolic sort of state, say it's malnourished over a long period of time, you tend to find that they're not producing a lot of proteins because they're utilizing all that protein for energy production, essentially, right? And so one of the things we can actually measure, there's different serum proteins. You guys ever heard of albumin? What's albumin do for us? Lots of things, but it helps. Sometimes it'll carry products, it'll carry things like drugs, it can carry all sorts of different molecules. It also helps to keep fluid within the bloodstream, essentially. But one of the things we actually measure for patients who are worried about malnutrition, we can actually measure albumin, because if the body's in a starvation state, your body's not thinking about making all these proteins. It needs ATP. It has to keep producing that, otherwise you're going to die. And so if in a malnourished patient, if they have low albumin, that tells us that they're probably not producing they're not getting enough proteins, they're not getting enough other macronutrients. We need to replenish that, otherwise they're going to continue kind of losing that, and there's other kind of issues that were kind of coming down the road. That sound about right?
Well,
to a degree, right?
To a degree.
Yeah.
Albumin and prealbumin are negative acute phase proteins.
Mm-hmm.
So that means
she sounds so much smarter than I do.
Decreased in a state of inflammation.
Yep. Sure.
So it could be malnutrition, but it could just be that they're in a state of inflammation.
100%, right? And so we see that a lot in like our critically stressed patients, like in the ICU, things like that. But that is again, different labs can be used for all sorts of different things. And again, you always have to look at with the clinical eye, say, okay, well, is this a malnourished patient, or are they someone who's in a critically inflamed sort of state? You can do that by kind of evaluating lots of other things. Anywho, but thank you for sounding very smart. I couldn't have said it better myself. Anywho, pull on your guys' perspectives and experiences, because it helps me to sound better on the video, right? Just kidding. Anyway, so another process here is called oxidative deamination. This is where we can utilize excessive amino acids. So if you had someone who's on like a really, really high protein diet, they could utilize some of these excessive amino acids for energy production. Some of that can also be stored as fat, some of that is glycogen, and also you can measure this in the urine as well, because a lot of this will get broken down to urea. This is a waste product that will be excreted within the urine. Okay. So again, any of our macronutrients can be utilized for energy. Our body prefers glucose in most cases. However, it can utilize other sources as well, depending on kind of the state the body's in. Okay. Again, looking at our different sources here, fatty acids primarily coming from the adipose tissue, lactic acid and amino acids primarily from the muscle, and then glucose and ketone bodies generally get produced within the liver. So again, kind of knowing kind of which organs are producing the majority of these different products that are utilized for energy. Again, just another picture kind of showing the same thing. You can see where each of these organs, what sort of byproducts they're producing, that they eventually get converted over into acetyl-CoA. And again, once you have that, then you can kick off the Krebs cycle, then you can kick off electron transport chain and produce ATP. Okay. So if you're deficient in one, your body can typically pick up the slack to some degree with providing it from some of these other sources as well, right? So again, it's all going to be kind of a balance. And again, if you have too much of any one of these, they tend to get stored as something else, right? So again, if you have too much glucose around, they can be stored as glycogen, but a lot of it also end up being converted as fat as well, right? So that's one of the primary things you see there. So you just know that lots of different sources, lots of different ways we can store these as well. Okay, and again, looking at different organs, you find they have kind of different preferences for what sort of energy they're going to be utilizing, or different kind of precursors. So for instance, the brain really likes glucose. And that makes sense, because if I have someone who's hypoglycemic, what's one of the first kind of signs they're going to manifest? Yeah, altered mental stats might be one. Like initially, they're going to be kind of hangry, right? They're going to be kind of aggravated and kind of anxious. But then eventually, as you get lower and lower blood sugars, they can develop altered mental status. You're like, man, why is the patient acting so funny? And then eventually they can develop what? Syncope, absolutely, right? So again, when you have a patient who's presenting with altered mental status or with syncope, one of the first things you check, and one of the first things that's very easy to get at the bedside, is we call point of care testing, right? POC testing. You ever see that point of care glucose or an AccuCheck is one of the first things you check, because if someone has a low blood sugar, is that easy to fix or hard to fix? Pretty easy. I just give them more sugar, right? I can start an IV, I can give them some dextrose, and boom, problem solved, right? All of a sudden they wake up, they're good to go. That's one of the first things you're going to do whenever you're kind of testing someone with altered mental status, is check their glucose. If that's low, you can fix that and correct it very easily. If that resolves all their issues, guess what? You save the day, they're good to go. They're still altered, they're still having syncope, there may be other things going on, but that is one problem you can at least fix early. Skeletal muscle, especially like resting states, they prefer fatty acids for their energy utilization. The liver likes to utilize things like fatty acid and ketone bodies. The heart can also utilize some fatty acids as well for energy production. Again, this is not so important to memorize, how many pluses are in each category. Just know that different organs are going to like different molecules better for energy production. They're going to rely on these on a higher degree. One thing I would probably know is that the brain does like glucose. If you run out of glucose, guess what? You're going to have some CNS issues.
If you're on a keto diet, does your brain not like that?
Well,
does it hurt your brain?
Well, so does anyone? I don't know if anyone's experienced a keto diet. I've not done it myself, but one of the things you kind of read about it is they kind of develop some manifestations of that. Because again, there's a period of time where when you drop, say, you go from like a carbohydrate-rich diet to one that is very low in carbohydrates, and they're usually getting like I think less than 5% of their total calorie count in carbohydrates. So again, it's pretty low. Amount of carbohydrates they're intaking. There's going to be a period of time where they get like pretty cranky because again they're going to be getting low amounts of glucose in the bloodstream and they're converting over to utilizing some of the other sources. So as they start to kick off things like lipolysis in order to produce new glucose, right? So it's not like a person in a keto diet has zero blood sugar because they would be dead, right? They're just relying on other sources to produce that glucose. So again, they're liberating fatty acids, they're liberating glycerol from the fat to go to the liver to produce glucose that the brain can then use. So there's a period of time where they may have some manifestations of that, but as their body switches over to try to maintain homeostasis, that glucose will kind of pick back up and then the brain should be fine, right?
It can kind of throw you into like acute kidney failure because it's really hard on your kidneys with all the ketones.
Yeah, you don't want to do that. Kidney failure bad, typically. She says it smart, and I simplify it, and then that's why we're such a good team there, right? Yes, sir. Which part?
The kidney part?
Oh, go ahead.
Oh, because of the ketones, like your body isn't going to be utilizing the glucose that you're eating. It's producing ketones, and your kidneys have to filter all of those ketones. So it can be really like put a heavy load on your kidney. And you can kind of throw yourself into acute kidney injury.
Yeah, so all things in moderation. Obviously, patients who have like pre-existing like kidney disease, they tend to be more likely to manifest things like that. But again, it all depends on your patient, right? Again, usually young, healthy people, like they can handle pretty high stresses, but if you have an older patient, and that's what I see probably more frequently than anything in the ERs. Like I'll never forget all the cases of like summertime in Florida, temperatures 105 outside, and people are like, I'm gonna get in shape. I'm 50 years old. I've never worked out a day in my life, and I'm super obese, and I'm gonna start working out with the best of them. I'm going to do CrossFit, I'm going to do keto diet all at the same time. Guess what? You're going to end up in the ER, right? Either with heat stroke, dehydration, acute kidney failure, rhabdomyolysis. I've seen it all, right? And so again, that's why everything in moderation. Take it slow if they have time. If you're dealing with a patient, who is obese or something like that, like you don't want to throw every single lifestyle change at them at one time, because guess what? They're probably going to ignore most of it. Most of it's either going to go over their head or they just stop listening. You have to do things, kind of baby steps, right? Always do things kind of incrementally. Hey, start with this. Maybe try walking 3 times a week for 30 minutes, and then you kind of build up from there to eventually they'll be CrossFit legends or something, right? Don't do it all at once. Anyway. Okay, so any questions on any of that so far? Fantastic. It's perfect timing. Let's do a 10-minute break. We'll come back and continue talking about the extracellular environment. All right, so any questions from the first half? ATP production. You guys have all been producing plenty of ATP in the meantime? Good. You guys store it up. You're going to need it the rest of the lecture. Anyway, so now we're talking a little bit about the extracellular environment. What is the extracellular environment? Everything outside of the cell, absolutely, right? So again, basically, and it's really kind of good to have a good understanding, kind of like what does the intracellular environment look like? What does the extracellular environment look like? And how can we affect that? How can we change that? How can we change things like fluid balance? How can we change things like electrolyte balance? Because that will have very strong effects on your physiology, and we'll go over some clinical examples as we go forward. But basically, we're seeing how can we regulate this? How can we change this, either with medications or with different types of therapies or different diseases? How can it all affect this? It's super, super important to understand kind of the basics here. So looking at how we break down our body fluid, you're going to find that roughly 67% of the fluid in your body is going to be in the intracellular space, right? So it's going to be actually located within the cells themselves, right? 33% of that we're going to consider to be our extracellular fluid, which can then be broken down into, say, 20% roughly is the plasma, and then roughly 80% is the interstitial fluid. Let's say interstitial fluid, what does that mean? Yeah, kind of the fluid like within the tissues, kind of around the cells, but not within the cells themselves, right? Because then again, that would be the intracellular fluid at that point. So again, roughly broken down into those components. Again, this can change greatly depending on things like what type of fluids the patient's intaking or not intaking, as the case may be. What is the tonicity of those fluids? We'll talk about osmolarity and things like that a little bit later on. But just know that roughly 80% of that the tissue fluid, roughly 80% of that extracellular fluid is going to be either tissue fluid or interstitial fluid, again, outside of the cells, but still, kind of directly affecting that. And again, the plasma is important because, again, that's what we kind of directly interface with things like if I give fluids via IV, where's it going into? Directly into the plasma, right? So again, this is going to be kind of the main interface we see when we have fluids being intaken from, say, like the GI tract. Where are they coming from? Or going into, I guess I should say, going into the plasma essentially, or if they're getting filtered through the kidneys, it's from the plasma. So again, this is the main place where things are going to be coming in and out of the system essentially, and then they can permeate back into the interstitial fluid, and then eventually into the intracellular space as well. Another way we can look at this, so again, what are our primary intakes for fluids within the body? Usually orally is going to be the biggest one, right? So when you drink a glass of water, that's your main intake you're going to see with that. The outputs are also going to be things we'll talk about. The main output being the kidneys, right? So again, when you have urine produced, that is your main output of fluid. But also you can have other things like what we call, remember, you ever heard of the term like sensible versus insensible losses of fluid? What's an insensible loss of fluid? It's going to be things you basically cannot directly measure. So for instance, when I'm breathing, am I just breathing off CO2? There's also some water vapor there as well, right? I can breathe off some water in those cases. Things like the feces or things like sweat, things I'm not really able to directly measure that well, that still contain fluids, right? When I sweat and have fluid evaporating off of the skin, I can't directly measure that. And one of the big things you're going to see when you're monitoring patients are going to be their I's and O's, or their inputs and outputs, right? So again, I'm going to be measuring how much fluid they're intaking via either IV or PO, via the oral route, and I'll be also looking at their outputs. Some of that I can measure, namely things like the kidney output I can measure pretty directly. However, things like, these insensible losses like the lungs and the feces I cannot directly measure as easily, and so I can't really account for that fluid loss in those cases. But anywho, again, this is going to directly interface with the plasma, roughly 3 liters. So notice it's a very small compartment compared to a lot of these other spaces here, but they're going to be going through the capillary membrane. That fluid can then interface with the interstitial fluid, which again is going to be kind of surrounding the cells, and then based on the cell membrane, some of the solute that's going to be dissolved in here can pass through, some may not, but that fluid can also interface with the intracellular fluid here, right? So again, there's always going to be these shifts. So when I give, say, a patient a liter of normal saline, right? So if I'm giving them IV fluids, it's going to go into the plasma, eventually into interstitial fluid, and then some of that will end up in the intracellular space, right? So if I someone who's like having a lot of vomiting, someone who's having a lot of diarrhea, they are fluid depleted. That's how I can try to tank them back up, essentially, is by giving them fluid back into the plasma. Okay. All right, so the extracellular environment, one of the big things we're going to see is that the plasma membrane, we mentioned, is going to be very permeable or not so permeable. When you're looking at like a cell membrane, that phospholipid bilayer. Typically more selective, right? It's going to not let just everything float by because, again, we're going to see that due to the fact that it has the hydrophilic head and the hydrophobic core, they're going to be preventing a lot of things from crossing over for the most part. Some small molecules can get across pretty easily, but you're going to find larger things tend to not cross so well. Things like proteins, things like nucleic acids, other big molecules do not go across that lipid bilayer very easily, which is a good thing because, again, we want to be selective in kind of what's going in and out of these membranes here. Generally, you're going to find that ions, so when I say ions, what am I referring to? Like sodium's a major one, some potassium, calcium, and again, we're going to see that things tend to go along the concentration gradient. It's going to be a big key component of this the rest of this lecture here, but things tend to flow along their concentration gradient. So things like sodium can enter into the cells pretty easily from the extracellular membrane, but nutrients, waste products can get out with some ease there. But that ability to cross is going to depend on lots of factors. We're going to look at what those factors are in just a second here. Okay, so membrane transport is an important thing. We'll talk about this a little bit in pharm as well, but this is one of those big things that are going to be affecting electrolyte transport. Is going to be affecting things like action potentials pretty significantly. Action potentials are going to be a big thing I'll be hammering on as we go forward, especially like in the neuro section and the cardiac section. A good understanding of action potentials and electrolyte flow are going to be very important to understand a lot of the physio here. But we're going to find there's different forms of transport that are happening across the phospholipid bilayer, right? So one of the first ones we're going to see is passive transport, and passive transport just means what? Do we know?
No energy is used.
No energy is used, right? It's passive. No ATP is being required for this process here, right? And notice that things are just going to be moving along the concentration gradient from higher to lower concentration, right? Without using any metabolic energies. No ATP is utilized in this process. This would be something that would just diffuse. You put a high concentration on the outside, it's just going to float across into the cell. And again, depending on several factors, that can be fast, it can be a slow process, but things are going to be moving passively, right? There's also active transport, and basically this is going to be active transport that requires ATP, and usually going to require some sort of specific pump or carrier protein within the cell membrane itself to move things along, right? So I'm going to mention passive diffusion. It's also going to be what we call facilitated diffusion. This is also passive because it does not require any sort of energy here. However, the active transport, this does require ATP. If you don't have ATP here, it's not going to work. We'll go over some good examples in just a little bit here. Let's see. So looking at the categories here, we mentioned that passive transport. Again, that's just things flowing along the concentration gradient. You can think about things like simple diffusion of lipid soluble molecules. They tend to cross that lipid bilayer with some ease, right? Because again, they can pass that hydrophobic core pretty well. Because again, things that are hydrophobic tend to be lipophilic, right? Because again, they're kind of different sides of the same coin there, right? So things that are hydrophilic tend to be lipophobic. So again, things like lipid-soluble molecules tend to have an easier time crossing here. You can have simple diffusion of ions across non-specific channels, right? So again, you can have different types of channels located within the cell itself that just allow ions to kind of flow. Or here's the example of the non-specific transport. They just kind of allow ions to flow along the concentration gradient. These are things that may not be able to cross the membrane themselves, but they can go through this transporter here. And again, no energy is required here. You have things like simple diffusion of water. It's called osmosis. Everyone's heard that term osmosis before. Very important concept here we'll talk about, especially when we're talking about osmolarity of the blood and things like that. But, especially when you're looking at things like the kidneys and how they regulate water balance and making sure that you don't just pee out all your fluids, because if you did that, you become dehydrated. It's not good. You need to regulate that sort of thing. And things like, aquaporin channels and other things that help to regulate water flow are very important, right? So depending on the organ and tissue you're dealing with. There's also a thing called facilitated diffusion. This is where you're going to have the transporter needs to be there at the cell surface to allow things to go through. It's still a passive process, but if that transporter is not there, things are not going to flow through. A good example is glucose, and that glucose normally does not cross the cell membrane by itself. It needs to have that transporter there to allow this to occur. It's still going along the concentration gradient, so going from high concentration to low concentration, just requires that transporter there, right? So it's facilitated, but it's still not active transport, okay? Active transport, though, needs energy, needs ATP primarily in order to cause this to occur, transport to occur. Now, we mentioned with all of the passive forms, or dealing with like facilitated diffusion, we mentioned those are going along the concentration gradient. If I have an active transport, does that still hold? Does it have to go along the concentration gradient? No, that is the main benefit of having active transport. It can go against the concentration gradient. And again, that's going to be one of the primary things we're going to see that it's mainly used for, is to use that energy to pump things against the concentration gradient, right? And that requires energy for that to occur. So again, simple diffusion, just crossing the membrane by itself along the concentration gradient. Simple diffusion through like a non-specific channel. You can just have proteins here that are just open that will allow things to flow through relatively easily. Now your body can control whether these are open or closed depending on different things. We'll look at some examples of that later on when we're talking about action potentials. And then there's facilitated diffusion that requires that transporter to actually, again, go along the concentration gradient. Glucose is a good example here, right? So that protein has to be there in order to allow for that process to occur. Okay. All right, so simple diffusion dealing with osmosis. Again, this is where we're going to be looking at the solvent, or basically what is going to be used as kind of the carrier fluid. In most cases, in our blood, it should be water, right? So again, I don't know if anyone has like alcohol-based blood. If you do, maybe you had too hard of a weekend. I don't know. Still recovering after Monday. Anyway, but yeah, so mostly the solvent is going to be water in most of these cases, and what we're talking about here. The solute is going to be all the stuff that's dissolved within it, right? So it can be our proteins, could be ions, could be all sorts of different molecules there, right? So that's all of our solute. And we mentioned that everything has to be kept in with a relative check within the body. So again, serum osmolarity is one of those things that has to be kept within a certain check. Otherwise, you're going to have different compensatory processes there to maintain homeostasis, right? So anyway, so normally when you're dealing with osmosis, you're dealing with solutes that are within a solvent, so again, or different stuff kind of dissolved in water. There's going to be kind of constant motion there of those molecules there, and again, they're going to want to go from areas of high concentration to low concentration typically. However, what would happen if I, say for instance, had just a completely permeable membrane here that allows the solute to float across? You would see that eventually over time it would go ahead and just equalize out, right? So again, have a high concentration on this side across the semi-permeable membrane. Over time, it's going to basically equate itself out, and I should be able to measure equal concentrations on either side of that, right? Everyone kind of familiar with that process? Again, it takes time, but it can occur just on its own. So, and again, if I were to put more solute into the solution, it becomes more concentrated, right? I'm going to have a higher osmolarity we're going to see. So again, solute concentration is going to be very, very important. It's going to be one of the things we're trying to regulate within the blood, as we'll see a little bit later on. Anyway, so again, this is again a passive process here. Now, for instance, we could also have, and again, this is another case of just kind of simple diffusion. Again, net diffusion is going to be going along the concentration gradient here from high concentration to low concentration. Stuff you've already covered probably several times before in your careers here. But again, when you have equal concentrations, is there going to be any kind of net movement of solute? Not at that point, right? Once it's kind of equalized out, once you have equal concentration on both sides, it doesn't really matter because you're going to have as much going in as what's going out, essentially, right? And do that random movement. Okay. Again, that net diffusion is that movement of solutes from high to low concentration. That diffusion time is can be equated as the mean diffusion time, basically just the average, how long it takes that solute to diffuse. It could be affected by things like, what type of membrane you're dealing with. It could be affected by what type of carrier proteins are needed for that. It could be affected by heat, different things like that. But that's basically just telling you the average time it takes for that equation or that concentration to disperse out and equalize in those cases. Okay, so osmosis, again, being another important concept, this is basically where we're having movement of water, essentially, right? And so we can do this through these channels called aquaporins. Okay, aquaporins are going to be very important, especially within the kidneys, to help regulate just how well we are able to hold on to water or get rid of water, essentially, right? So, for instance, if you're in a dehydrated state, what do you notice about your urine? Usually darker colors, more concentrated. It's usually the volume is less or more than if you're in a very hydrated state. Usually a lot less, right? So again, these are kind of common sense things you guys have dealt with all through your lives. But again, usually you're going to have a more concentrated urine, and it's going to be smaller in volume. And that makes sense because, again, if your body's in a state where it wants to hold on to fluid, it can do things like increase the amount of aquaporin channels that are available to allow for reabsorption of water, right? And again, we'll get into more detail in the kidneys later on. But again, these are these concepts that are happening here to try to regulate things to make sure that if we're in a state where we're dehydrated, we try to hold on to as much fluid as we can. Versus if we're in a very hydrated state, what do you notice about your urine at that point? Clear, like very straw colored to clear colored, very dilute, and the volume is typically much higher, right? Absolutely. So again, very in kind of common sense sort of things we're dealing with there. You're going to find aquaporins are also really important in places like the eyes, right? So again, this can be important in helping to regulate things like pressure within the eyes, and we know what you call it when you have high pressure in the eyes. Glaucoma, right? So again, that can be an important thing that can be affected by things like aquaporin channels, the lungs, salivary glands, the brain. They kind of reside everywhere in order to maintain a proper fluid balance within these different tissues, right? And so, for instance, if you have too much fluid on the brain, what do you call that? So usually when you have like fluid buildup somewhere, you call that, starts with an E, edema, right? So if I had it in the brain, it would be called cerebral edema. Anyone ever heard of that term before? You ever heard of like someone who like gets into a car wreck, bangs their head, and they have cerebral edema, caused swelling of the brain? Like those are things that we can see can be kind of negative effects of osmosis and things we can try to affect by different therapies we're going to administer for those patients. But anyway, so this is an important process to make sure we're kind of regulating fluid balance, because if it gets too much in one area, that's when you have edema form. That's usually not a great thing. All right, so looking at water movement during osmosis. So again, this is basically that net movement of water. And again, typically water is going to, again, go along this concentration gradient. But what you notice clinically happening here is that you're going to see that typically when you have a low concentration of something, water, you're going to find that it's going to be moving to the area of higher solute concentration, right? Because again, if you have a higher solute concentration, there's less water there essentially. So the water's going to want to flow along its concentration gradient to dilute that out. So for instance, if you were to look at this selectively permeable membrane, notice here you have a higher solute content here within section A. This is only going to be permeable to water. You're going to notice there's going to be a net flow of water in this direction. You'll see water leave one area and go into another. So for instance, I can actually do that clinically. So for instance, I have that patient who banged their head. They have cerebral edema. They're building up fluid in the brain. I can actually give them extra solute in the blood. So I put a lot of extra, say, like salt, for instance, I put extra solute in the blood, and I can actually draw water off of the brain and relieve that pressure, right? The brain doesn't like really high pressures there. You can actually kill them. So by pulling that water off, I can help to relieve that pressure and then fix my patient, right? So these are just examples of how you can use this stuff clinically, these principles of osmosis, essentially. So again, osmosis, that water moving from an area of low solute concentration to an area of high solute concentration. Okay. So again, imagine you were to have, for instance, you have this ball here that is only going to be permeable to water. So you have a low glucose concentration here, or sucrose here, 180 grams per liter versus a very high concentration here. Where do you think the water is going to flow? It's going to flow into this, past this membrane here. It's going to flow into, and you're going to find that this is going to swell, right? So water is going to want to go to the area of higher concentration to dilute this stuff out to eventually equal, have an equal concentration between these two, right? So looking at this case, if you were to have, say, a low concentration, or this 180 grams per liter of sucrose versus 360 here, you're going to notice that the higher pressure is going to be, you're going to find more osmosis occurring here with the higher concentration one. So see, this is basically your pressure reading here. Notice because it had a higher concentration to begin with, more water flows in versus this area of lower concentration sucrose. That kind of makes sense? So more water's flowing in, that makes more osmotic pressure. That's a good term to remember. Like, osmotic pressure helps us to determine where water is going to be flowing to, right? So for instance, if I have a case where my patient's really dehydrated and they have low intracellular fluid concentrations, if I want to replenish that, I can do that with osmosis. And I'll show you some ways we can do that a little bit later with our fluid selection. And actually, one of the biggest things you're going to do if you're ever admitting a patient to the hospital is deciding what type of fluids you want to give them. If they're NPO and they can't take in anything, you want to decide, okay, well, do I want to give them, free water? Do I want to just give them plain water, or do I want to give them something with some solute in it? The answer is you never want to give them free water. But you want to, do I want to use normal saline? Everyone's heard of normal saline before, right? We'll talk about why normal saline is normal, but there's also half normal saline. There's hypertonic saline. There's all these different things you can administer, and it's important to select the right one for your patient. Otherwise, you're going to cause osmosis to kind of go haywire, essentially. Okay. We'll go some more clinical examples here in a second. Okay, so looking at plasma tonicity, and I'm going to use osmolarity and osmolality incorrectly. I'll probably use them interspersed. Anyone actually know the difference? Clinically, it doesn't matter, right? I'm going to use them interchangeably. I'm probably going to use them incorrectly. Don't correct me, it's fine. We'll get the same point across regardless. So, anywho, looking at the plasma osmolality here, you're going to see basically a 0.3 molar glucose or a 0.15 molar sodium chloride solution here, right? So basically, what you're going to find is, and this is the key point here, is that normal serum osmolarity is between 275 to 295 milliosmoles per liter. Okay, memorize that number is not super important here for our purposes, but just know that this is there's a normal serum osmolarity we're trying to maintain, and that if you go beyond this, if you try to get too concentrated or too dilute, you're going to find that there's going to be some compensatory changes that happen here, especially like on the endocrine side of things, some other things. Now, for instance, if I were to say add more solute to the blood, say add a whole bunch of salt into the blood, what do you think that osmolarity is going to do? Go up or down? Tend to go up, right? Because I add more solute, there's more osmotically active particles there in the blood. This is going to go up. However, for instance, if I were to say add more water to the solution, what do you think that would do to the osmolarity? That would actually decrease, right? As you make the solution more dilute, that's going to cause the osmolarity to go down, right? And so again, we can affect that. If I have someone who has a high osmolar blood, if they have a very concentrated blood, the body's going to want to try to add more water to that. Right, and so it's going to want to try to maintain that balance there as best it can and get that osmolarity back into the right kind of range there. Okay. Now, what we'll mention is there's going to be things that are isotonic, which means that it is going to have the same concentration essentially as what the other kind of competing solution is going to be. So for instance, say we're dealing with a red blood cell here, right? So if we have the same concentration of solute on the outside of the blood cell as on the inside of the red blood cell, there should be no net movement of water here, right? It's called an isotonic fluid. They share the same concentration of solute across either side, okay? So the water going in is the same amount as the water going out. No change there, right? So for instance, when we're looking at isotonic fluids, this is good because it helps to prevent fluids from shifting greatly. So for instance, if I have a patient who has, say, their plasma volume is decreased, but I don't want to increase, say, like their intracellular fluid necessarily, I can give them something that's going to be isotonic. I should see no net movement of fluids. So for instance, if I have, say for instance, I have a patient who is their plasma is depleted, what do you think that's going to do to their blood pressure? Again, the plasma is what's filling up your blood vessels. If you're losing all that fluid, pressure would probably decrease, right? So again, if I have someone who's hypotensive and I want to give them fluids to try to bring their blood pressure back up, I want to give them something that's going to stay right there within the plasma. And so I can do something that's isotonic that's not going to cause any kind of fluid shifting to occur. And so this is why we give what we call normal saline. If you ever see normal saline, it'll also be called 0.9% sodium chloride. So the question is, why do we use 0.9%? Why is that normal compared to what our body is normally producing as far as osmolarity goes? Well, I can show you right here. Basically what happens is when you see this, is that there's 0.9 grams, and again, these numbers aren't specific to memorize, but when you see 0.9%, what that basically means is there's 0.9 grams of sodium chloride, So again, just normal table salt and 100 mLs of water. Okay, so that is why we call it 0.9% saline. Again, the other name is normal saline. Sometimes if I have patients who are coming in who are seeking drugs, like they're seeking like morphine or Dilaudid, an alternative drug I will offer them is called normazoline. Give them a liter of that, they typically feel better and they don't know any different, right? Some of them are a little more savvy than the other, but if you're hearing normazoline, that's what I'm referring to. Anyway. There's also other types of isotonic fluids as well. Anyone ever heard of lactated ringers? Yep, so lactated ringers typically gets used in the surgical realm more frequently than normal saline. If you're in the ER, you see a lot of normal saline being used. If you're in surgery, you see a lot of lactated ringers. And again, this is another one that's going to be isotonic. So again, we said, normal serum osmolarity is around like 270 to 290-ish. When you're looking at normal saline, if you were to break it into its constituents, sodium and chloride, you notice here that you can break it down to 154 milliequivalents of sodium and 154 milliequivalents of chloride. When you add that together, that's all the osmotically active particles. That's 308. Pretty close to what the actual normal serum osmolarity is, right? So that's why I call it normal saline. It's pretty close to what a normal serum would be. Lactated ringers is even closer. I see this around 273 milliosmoles per liter, right? So again, that's why they like to use that in surgery. There's some other reasons I'll talk about later on, but basically we like these because they do not cause a lot of fluid shifts. If I put this into the plasma volume by giving it in the vein, it stays right there. Helps to kind of tank up the intravascular space, and it's going to help them maintain their blood pressure and things like that. That make sense so far? Okay. When I say normal saline, that's what we're referring to. Now, if I were to say, hey, half normal saline, what do you think that would be? Yeah, 0.45% sodium chloride. And so you'd actually see that that would be a more dilute solution. We're going to find out what that would do when you're using something that's hypotonic, right? So again, that's going to be one of the other things we'll talk about here. So let's say we have solutions that are lower in solute content. These are going to be what we call hypotonic solutions. And basically, if I were to infuse a hypotonic solution, that actually will end up drawing water into the cells essentially. So for instance, imagine here I have my red blood cell, and I say I have a low so I have a low solute concentration on the outside, but it's higher on the inside here. So this water surrounding is hypotonic compared to the red blood cell. You're going to find that waters want to go via osmosis to where the solute concentration is higher. So it's wanting to go into the cell and cause it to swell, right? So again, that's where you can see cellular swelling occurring is when I give a hypotonic solution. And again, that's a big reason why we never give sterile water into a patient, because that solution has no solute in it, and it's going to cause all that water to go into the cells and cause them to swell. And what happens when cells swell? Eventually, they burst. Do we want our cells to burst? Not typically, right? They're not water balloons. We don't want them to burst open. So we never give really strongly isotonic fluids, right? Or again, this would have no tendency to it whatsoever if I were to give sterile water. We use it for other purposes, but not for patients. And actually, I mentioned the Joint Commission before. There's different regulatory bodies that help to maintain accreditation for hospitals, but one of the big things they look at is medication safety, and this is one of the big things they see is to make sure sterile water never leaves the pharmacy, because if they see it out on the floor, it could be accidentally given to a patient, and that can kill them potentially, right? So again, you never want to do that. So again, isotonic fluids cause water to shift into the cells. All right. Now, if I were to have something that has a higher solute concentration, that would be what I call hypertonic, right? So it's a very high concentration of solute in there. And what you end up finding is this actually draws water out of the cells typically. So very high concentration of solute here. Water's wanting to go to the area of high concentration of solute. So it's going to go cross over. And then you're going to have my cells start to shrink. Or anyone know another term for that? Crenate, yes. So your cells are going to crenate. This is what I was referring to when I'm talking about a patient who has cerebral swelling or cerebral edema. I can give them a hypertonic solution, and that actually helps to draw water off of the brain and help to relieve that pressure, right? That's something you may see very frequently if you ever work in trauma or deal with any of those type of patients. That will give hypertonic saline in order to do that. And so, for instance, we use 3% normal saline. We mentioned normal is what? And normal is 0.9, so we're using something that's more than 3 times more concentrated and using quite a bit. So again, 513 milliequivalents of sodium, so quite a lot of sodium here. Very high osmolarity. It's very good at drawing fluid off of those spaces. Right? So you can see other cases where edema is forming. This helps to draw water off of that as well. Okay. So hypertonic fluids draw water to it. Hypotonic fluids usually draw water away from it. Okay. Isotonic should draw water nowhere. It should be equal movement in and out. Okay. Fantastic. So again, just another picture kind of showing what's going on here. So imagine we have a membrane here we're going to be putting into, say, a hypotonic solution. This is going to cause the cell to swell. Or to put it into an isotonic fluid, no change should occur here. So again, the solute concentration is equal between the outside of the cell to the inside. And if I were to put it into a hypertonic solution, so a lot of solute here, it's going to draw water out of the cell. Okay. And so you can kind of see in this picture here what's kind of happening. So imagine I have my patient. I'm looking at the extracellular fluid here in the yellow, and we want to see my intracellular fluid here in the red, or the kind of pinkish sort of color here, right? So again, if I'm looking at my osmolarity, usually let's say around 300 or so for a person, and then I'm looking at the actual volume in liters I'm seeing here. So imagine I were to give, say, an isotonic sodium chloride, so something less than, isotonic would be 0.9%, right? So notice here that there really shouldn't be any increase in the intracellular fluid, because again, it's all going to stay where I put it, and I'm putting that sodium chloride into the extracellular fluid, right? I'm putting it into the intravascular space where it stays right there. So notice this volume increases, which is good if you have like a hypotensive patient. You can help to increase their blood pressure by increasing the amount of volume that's within the veins and the arteries, right? That's a good thing. If I were to give, say, like a hypotonic fluid, notice here that it's going to cause the water to go into the cells, right? And so I can see what's happening here is my intracellular fluid volume is going to increase. I'm going to see a little bit of increase here on the extracellular side as well. But what do you notice about the osmolarity? Is decreased from where it was, right? Because I'm giving a hypotonic fluid, something that has a lower concentration. So for instance, if I were to give, say for instance, half normal saline, that is 0.45%, I'm going to find an increase in my intracellular and extracellular fluid there, right? The tonicity may go down a little bit, may drop my serum osmolarity, but I should see increase in that fluid volume. On the other hand, if I were to give, say, like a hypertonic sodium chloride, say like a 3%, you notice that the intracellular fluid does what? It's going to shrink in volume essentially, right? So I'm going to cause that fluid to go out of the intracellular space and go into the extracellular space. That's how I draw that fluid off of the brain essentially when I'm talking about cerebral edema. And then you notice the tonicity is going to do what? It's going to increase, right? The osmolarity is going to increase to that solution because I added a hypertonic sort of fluid, right? So if I did 3% saline or something else that was hypertonic compared to the blood. That makes sense? So again, isotonic fluids cause no water shift to occur. Hypotonic fluids usually cause the fluid to shift into the cells, and then a hypertonic fluid will usually cause water to come out of the cells. Those are key points to remember. And again, like I can kill patients if I'm giving the wrong type of fluids here. So if I give someone, a very hypotonic solution, I can cause those cells to swell and start to burst. That's not good. Versus if I were to give a very hypertonic solution, that cause all kinds of other problems on the flip side of that, causing your cells to swell and then potentially start to have damage due to that, right? Okay, so looking at common IV fluids, and again, these numbers are not things to memorize, but it's just to kind of give you an idea for common fluids you're going to see being used in the clinical realm, right? So for instance, when I'm talking about normal saline, this is sodium chloride 0.9%. Notice here the pH a little bit lower than what our normal serum pH is. A lot of that's due to the chlorides kind of floating around in there. But notice here, it's going to be isotonic to the blood essentially, right? So maybe a little bit hypertonic, but mostly isotonic. We'll consider that. Also notice if you look at a serum sodium, I should say, a normal serum sodium. Anyone know what that is off the top of their head? Usually around 140. So again, this is a little bit higher sodium than we would normally give, but it's pretty close to what our normal serum sodium is. So you really shouldn't have any issues if I give normal saline. You're very unlikely to cause big problems if I give a patient normal saline. If you give them too much, that can be a problem. But again, if you use normal saline, you really can't go wrong in a lot of cases. On the flip side of that, imagine we were to give dextrose. Right? Because again, if patients are hypoglycemic, I want to give them some dextrose to try to help their blood sugar out. Notice here that the osmolality is pretty low. So you would consider this to be what? Yeah, it'd be hypotonic compared to the normal serum osmolarity. So if anything, you'd actually find more fluid going into or out of the cells. Into the cells, right? And so actually we call this a lot of free water because most of this is going to end up, especially as that glucose gets metabolized, ends up out into the intracellular space. So you see some cell swelling that can happen with that. So more frequently, what we'll do is we'll give dextrose along with sodium chloride. So has anyone ever heard of like D5 half or D5 normal saline? That's what we're referring to as a mixture of dextrose, usually in a 5% solution, and usually sodium chloride, whether it be half normal saline or just normal saline. And so what's nice about this, when you combine these two, you notice that the tonicity is going to be a little bit higher, and this can be useful to kind of help prevent those kind of dangerous fluid shifts that occur there. Okay. Mentioned lactated ringers is going to be a very frequent one you're going to see used in the surgery realm, and that's because it tries to look a little bit more close to what the actual serum ions actually look like. So notice here sodium's around 130, potassium's around 4, which is a normal serum potassium level, things like that. So again, they try to give that because it's a little bit closer to what the actual human serum really looks like. But so those are the main takeaways. So just know what's going to happen if I give an isotonic fluid, a hypertonic fluid, or a hypotonic fluid. What happens with that fluid shift there. Okay. Just know these are going to be some common fluids you're going to run into in the clinical realm. So again, plasma tonicity, isotonic solution see no shift. If I give a hypotonic solution, cell swelling, hypertonic cell crenation occurring there. All right. So the other thing to note here as well is in regards to like transport of solutes and transport of ions across the cell is to note kind of what the normal concentrations kind of are. And again, you'll get familiar with these as you go along. And if I ever have like a lab value on a test, I'm going to give you the normal range so you can make an interpretation about it. I don't want you to memorize that normal values right at this point, but I do want you to be able to make an interpretation of something low, high, or normal essentially, right? So one of the big things I always remember about the cells, and this, my wife actually taught me this, is she says that you can just think about your cells as salt-wrapped bananas. Like salt-wrapped bananas, what does that make? It makes no sense. It makes a little bit of sense. So imagine the sodium on the extracellular fluid side, it's around 140-ish milliequivalents per liter. That's a normal concentration of sodium within the body on the extracellular side. So if I measure the blood, I'm measuring the extracellular fluid essentially, right? Potassium, usually around 4. So does that mean there's a whole lot less potassium in the body than sodium? Not really. What it really means is that there's a very high potassium concentration on the inside of that cell, right? So again, roughly the flip of what we see with sodium here. Very low sodium concentration on the end of a cell, on the inside of a cell. Very high concentration of potassium, right? And what food is high in potassium? Bananas, absolutely, right? So again, that's why I say salt-wrapped bananas. So a lot of sodium on the outside, a lot of potassium on the inside. And this is very important when you're trying to kind of figure out what's going on with things like action potentials in the neurons, in the cardiac cells, all those sorts of things. This will come back and kind of bite you in the butt if you don't kind of understand this at a minimum here, right? And so, for instance, say for instance I had a channel that was receptive to sodium. Which direction do you think sodium would flow on say the cell membrane? Yeah, so again, via passive diffusion, it would flow to the inside of the cell. And that's one of the big things you're going to see, especially when we talk about action potentials, is that sodium likes to flow into the cell, potassium likes to flow out of the cell. If you disrupt that, that's where it can have some issues that can come about. We'll talk about later, right? Other important things like calcium is very, very important. Notice here, calcium levels, very, very small in the intracellular fluid. However, if you look at like the skeletal muscles, like they have a ton of calcium in them. But you remember where he said they get stored at? In the sarcoplasmic reticulum. That'll come back again when we talk about muscular function. A lot of calcium stored there. So even if I were to measure the fluid within the cell itself, I wouldn't measure much calcium. However, when I open up that sarcoplasmic reticulum, it all floods out. And then when it's done, it can flow back into that, right? Obviously, magnesium is important here. Chloride, bicarbonate. This is important. Why do we like bicarbonate? Manages pH, right? It helps us as one of our buffers here that helps us to keep a normal pH within the body, right? So I think glucose obviously should be, in abundant amounts. Cholesterol we'll talk about later on. And some other things. So normal pH, usually a little bit more acidic within the cell, usually due to metabolism occurring and it's producing CO2. So that kind of makes sense why it'd be a little bit more acidic in there. But okay, so anyway, so we'll kind of get into these and why they're important a little bit later on. I'll show you some examples. All right, so remember, as far as transport goes, typically it can either happen via simple diffusion, right, just going through the lipid bilayer without any really issues here. It could be going through a channel protein, which kind of open and just allows it to come along, or it could be facilitated diffusion. I mentioned glucose being a good example of that. And then the other ones we'll talk about being energy dependent, requiring ATP, are going to be these active transports. And remember, what was the important thing about active transports? Yeah, so they require ATP and they go against the concentration gradient, right? So for instance, in this case, when I'm talking about sodium being higher on the outside and lower on the inside, an active transporter would do what with sodium, potentially? Pump it out of the cell, right? So again, it could pump it against the concentration gradient, but that requires energy, right? If I was just doing it passively, it can only go into the cell via its concentration gradient. Make sense? Okay, cover this ad nauseum as we go forward, trust me. Okay, so the question is, how do we regulate our blood osmolality? How do we make sure that we're having fluids, going right where they're supposed to? The hypothalamus is one of the big places that helps to regulate this. This will be, we'll talk about this more in the endocrine section in just a little bit. However, we're going to find that if you have a high plasma osmolality, usually due to things like dehydration, or say someone's like abusing diuretics and they were losing a lot of fluids in the urine, or they're vomiting, or having lots of diarrhea, or say they were bleeding, that can sometimes lead to a high plasma osmolality. And so what happens when you get dehydrated? You get thirsty, right? Your brain says, hey, we should probably get some more fluid in here to try to dilute the blood out, try to get that osmolality back down to where it should be. And so that's why you get your thirst responses that get activated. Anyone know a hormone that helps with that? I was talking about ADH. Anyone ever heard of vasopressin or antidiuretic hormone? That's going to be a really important hormone we're going to talk about in the next section here as well. That is going to increase our thirst response. So say, hey, try to get lots of water. And then it's also going to decrease the amount of water that gets lost in the urine. So it can help to concentrate the urine, hold on to more fluid, and also helps us to think, hey, become more thirsty. And try to get some more water. And if you have a low plasma osmolality, usually your ADH will be decreased. because again, those negative feedback loops, remember that, you're going to find there's going to be more water excreted in the urine. So there's disease states that can occur when either one of these are kind of out of whack. And so one of the things you'll see if you work like in a surgical ICU, especially with head trauma patients, is they can develop a condition called syndrome of inappropriate antidiuretic hormone, or SIADH, if anyone's ever heard of that. And they secrete a lot of ADH. And one of the things that's really interesting is that one, they have really concentrated urine, because their body's trying to hold on to that fluid. But the other thing is that thirst response gets activated very strongly. And so again, when I get thirsty, I have to go and drink some water, right? These patients, though, their blood is so dilute, right, because they have too much ADH floating around, that I don't want them to get any more dilute. I don't want them to intake any more fluid. However, their thirst response is going crazy. So we have patients who are like trying to sneak out of the ICU just to find water anywhere, right? If they find some Gatorade, they will lie, cheat, and steal to get their Gatorade. They will try to bribe their family members to go down to the cafeteria and bring them back some water. That's the only thing they want in the world, right? Because if you've ever been like really, really thirsty, these patients are like that times 10. And so we'd have to basically lock down the room to be like, okay, no one's allowed to bring them any water, because we have to get their electrolytes and their osmolality back into check there. So again, very interesting kind of things that can happen when you start to mess around with this osmolarity. So anyway, but the kidneys are a big place we regulate this, and then the brain's the other big place with those thirst centers there. But the hypothalamus kind of controls everything. We'll talk more about that a little bit later. Okay, so then looking at simple diffusion, you can find that as this occurs, usually kind of non-polar lipid-soluble molecules have an easier time going across, right? So we said non-polar tend to be things that tend to be a little bit more lipid-soluble anyway, but things like oxygen makes sense, because if you look at an oxygen O2 molecule, again, it's non-polar because they're very equal in respects to their kind of their orientation, their stereochemistry. Carbon dioxide can cross pretty easily as well. And that's important because we want to have normal diffusion of gases across these membranes here. So that way we can allow for oxygen as we deliver it to the cells to go in. Because again, these things are going along or against the concentration gradient with simple diffusion. Along the concentration gradient. So as I deliver oxygen to the tissues, which have utilized most of that oxygen during what? Where do we use all our oxygen? Cellular respiration. So as I utilize that oxygen and develop a lot of CO2, as I deliver new oxygen to the tissues, I can have that oxygen disperse out to the tissues. And now carbon dioxide is in high concentration out there. It's going to diffuse back into the red blood cell, and then I can deliver that to the lungs, and I can then breathe that off, and then there you go, right? So again, everything is going along the concentration gradient. No energy is required for this process to actually occur here. One example of that actually occurring there. Other ones where you can have diffusion across those membranes. So again, charged ions typically would not cross that lipid bilayer very easily, right? Because again, usually a charged ion like that tends to be more hydrophilic or lipophilic. Very hydrophilic, right? Because again, it has a charge on it. It likes to be in water, essentially. It would not be able to cross this lipid bilayer very easily at all. And so it needs these transport channels here, which can open up and allow sodium to flow across, right? For instance, or it could potentially allow things like potassium to flow out. Always going to be along the concentration gradient. And this is important for things like resting membrane potential. We talk about action potentials. It's important for cardiac function. It's important for neuronal function. Lots of things. The other big thing with the fusion there is that if I close the channels, it's going to stop things from flowing across. If I open the channels, it allows things to flow. So again, the body has some control over that as well. Facilitated fusion is not going to require any ATP, but you have to have those transporters there to allow things to go across. This is usually a very specific sort of thing versus those channels in the last slide may have been non-specific to allow either sodium or potassium to go through. These typically are going to be a lot more specific to maybe like glucose or to other hormones or to whatever else it happens to be. Okay. And again, these are all going to be along the concentration gradient. So again, if I have high blood sugar and I have these channels present on the membrane, I'm going to allow for that glucose to go along the concentration gradient. It doesn't take any energy here, but it goes along and gets into the cell where it can be utilized for ATP production. And then facilitated diffusion here, you'll notice that there, depending on the tissue you're dealing with, there can be different types of transporters that happen. So for instance, with glucose, there's varied types of glucose transporters depending on the tissue you're dealing with. And again, you don't have to remember, memorize which GLUT transporter is in which type of tissue, but just know that they're all a little different and they can respond differently. So for instance, in the pancreas, we want to have one specific type of glucose transporter that may not respond the same way that it would in, say, in the CNS, or may not respond the same as it would, say, in the neurons, okay? But they allow for, they may be expressed in different periods depending on what's going on in the body. They're all a little bit different. But again, there's going to be some variability there in different tissues. Okay, and there's also active transport, and again, with active transport, typically things are going to go against the concentration gradient for the most part. And so, for instance, with these calcium pumps, with the sarcoplasmic reticulum we mentioned, it's usually found in skeletal muscle cells. We'll find when we talk about muscular function, the calcium is very, very important for a muscle to contract. But when all that calcium gets released, you got to pump it back into that sarcoplasmic reticulum. We don't want it floating around forever, because if I had that occur, the muscles can never relax, and that can cause something called rhabdomyolysis. Anyone ever heard of that before? What is rhabdo? Muscle breakdown, right? The muscles are too tense and contracted, and they eventually start to break down. That's no good. So we need things like active pumps to pump calcium back in against the concentration gradient, and that does require ATP. You have to have that in order for that process to occur. Okay. Another big active transporter we're going to talk about that flows ions. Anyone ever heard of the sodium-potassium ATPase pump? You're going to know that very well by the end of my class, because I talk about it all the time, because it's very, very important for all sorts of different functions. Okay. So again, this allows for good, strong contraction, but then when your body says, hey, I don't need to contract this muscle anymore, it allows it to relax by getting rid of that calcium back into that sarcoplasmic reticulum. Okay, again, active transport pump. Here's an example of, say, antiporters. These are going to be things that are going to be moving things in opposite directions. So, for instance, here's one that's going to be moving sodium into a cell versus calcium moving outside of the cell. So we call these counter transporters. You see this very frequently in the kidneys. This helps to regulate things like reabsorption of certain ions or secretion of certain things. Here's one that does sodium plus hydrogen ions. This is going to be important for maintaining balance of pH, especially in the kidneys. So this will come back up later. But just know that there's different functions for different transporters depending on the tissue that you're residing within, right? Okay, sodium potassium ATPase pump is super, super important. You're going to find it all throughout the body. A lot of it is very important for things like the neurons, for cardiac cells, for those to function appropriately. Very, very important. And so, again, one thing I would strive to remember for your purposes, because again, this is just going to come up in CMS, and come up in pharm, come up everywhere, is that the sodium potassium ATPase pump is shuttling sodium and potassium against the concentration gradient. So it's moving sodium into or out of the cell. Out of the cells, we already saw, because we know that outside of the cell has a higher concentration. So we're pumping usually 3 sodiums out, and it's going to be pumping 2 potassiums into the cell, again, against the concentration gradient. This is really important because it helps to maintain normal resting membrane potential. Anyone ever heard of that term before? It'll come up again when we talk about action potentials later on, but it's important to make sure that your neurons and your cardiac cells and everything are at appropriate electronegativity. If not, you can find things, bad things can happen. Seizures can happen, arrhythmias can happen. You need to have this pump working appropriately to help maintain that membrane potential. So again, we'll talk about this much more detail later on. Again, usually going to be pumping 3 sodium out, 2 potassium in, and resets that resting membrane potential to allow for additional action potentials to occur later on. Because again, when you say activate a neuron, you want to be able to activate it again later, and that's important. You make sure you maintain that resting membrane potential, right? And again, requires ATP. If you don't have ATP around, guess what? It's not going to happen, right? So again, you need to be able to make sure you have ATP available. Otherwise, this pump doesn't work, and you can't attain that resting membrane potential. Here's another picture kind of showing the same thing, utilizing the ATP here. Again, ADP gets produced again because that can be reutilized in ATP production later on in the cell. Again, potassium is going to be going in the cell, sodium is going to be going out. Okay. Do you guys want to hear a joke about potassium? Okay. You want to hear one about sodium?
No.
Nah. I didn't think so. All right. So membrane potential. Super important concept here, right? So there's a difference in charge on each side of the plasma membrane, right? And this is mainly due to the fact there's a lot more negatively charged molecules on the inside of these cells than there are on the outside, right? So again, you're going to find there's a relative positive nature on the outside of the cell, and there's going to be relatively negative on the inside. And there's a potential difference here, and we call that the resting membrane potential, okay? Maybe a little bit different depending on the type of cell you're dealing with, but it's important that we maintain this. Otherwise, you're going to find that you're not able to appropriately have things like action potentials occur, right? And this is maintained because, again, with these cells, you may find there's some passive amount of sodium flowing into the cell. There may be some passive potassium flowing out, but you need to maintain that balance by using the sodium potassium ATPase pump. This is the biggest thing we have to make sure we maintain that balance between sodium on the outside of the cell, potassium on the inside of the cell, right? And again, always going against the concentration gradient. And again, this is working in direct opposition to this kind of passive transport of sodium and potassium, okay? And we'll look at their specific functions in regards to action potentials and cardiac function later on as we get into the individual organ systems. But again, this is kind of the baseline for what we're going to use to expound upon later on. Okay, usually you're going to find that a lot of the resting membrane potential of a lot of these cells tends to be a negative 90 millivolts. By maintaining negative 90 millivolts, you can have things like ACT potentials come along and actually activate those cells. See what that looks like a little bit later on. But again, this has to be maintained, usually negative 70 to negative 90. And by altering this, you can actually see things can occur. You may either be able to make the cell more likely to have an action potential or less likely to have an action potential. So for instance, if I were to have, say, a cardiac cell that is too active, say for instance I raise the resting membrane potential from say negative 70, say up to negative 50 or negative 30, that makes it more likely to have an action potential, makes it more likely to fire off. And you know what happens when the heart is abnormally firing off action potentials? It's called an arrhythmia. And the heart really can't pump blood very efficiently if it's having an arrhythmia, and that can lead to all kinds of issues that can occur, right? So same thing can happen for neurons. What happens if a neuron's firing too erratically or too often? You can develop seizures, absolutely. So again, that's one of those things where we can directly affect this either with disease states. We can affect this with medications very frequently. That's where I deal with these a lot in order to make these cells either more active or less active. And it's based on altering this resting membrane potential, right? Again, usually you're going to find that the anions, which again, anions are usually negative, cations are positive, right? So again, the fixed anions, these you can't really change this all that much, but what I can do is affect the electrolyte flow. I can affect how well the electrolytes are going either into or out of the cell, and by doing that, that's allowing, by changing the positive, I can affect that resting membrane potential and either make it more positive or more negative. And that can affect the function quite dramatically, as we'll see when we get into some specific examples. Okay, you're going to find that also some other ions as well can contribute to this. So things like calcium, chloride can also contribute to the resting potential. But you're going to find that typically when you're having flow of these ions across, the biggest things are going to be changing here are going to be sodium, potassium, and chloride. Those are going to be some of the biggest ones that are going to have big effects here. Calcium will also play a role there, especially in the heart. We'll see that's going to be another big player. And again, if you're at resting membrane potential, that's when you're at the cells at rest, basically. You're not actually having an action potential being propagated. Usually when the action potential comes along, it's going to actually increase that electronegativity. It's going to become usually either less negative or positive in some cases, as we'll find as we go along. But again, all of this is going to be related back to that shift of electrolytes either in or out of the cell. Okay. So again, looking at this, you're going to find that typically potassium is going to be the main positive cation is going to be within the cell. You're going to find sodium is going to be the major one on the outside. Typically, chloride is going to be a thing balancing out sodium on the extracellular space, and then calcium tends to be present within the extracellular space, but most of the time it's going to be sequestered within the cell into usually things like the sarcoplasmic reticulum or other storage sites like that. Because calcium is actually a really good messenger molecule. We're going to see when we get into secondary messengers later on that's very good for helping to activate different biological cascades, as we'll see later on. So for instance, like calcium is really important for not only muscle contraction, but also for causing clotting to occur and causes things like insulin to be released from the pancreas, causes neurotransmitters to be released from neurons, all sorts of things calcium helps to do. And that's why we want to keep it really tightly sequestered within the cell. Okay, so what occurs when you have an action potential? How much time do I have left? I have 1 minute left. Do you think I can cover all of the action potential in 1 minute?
No.
I don't either. I don't think so. All right, so I'm going to go ahead and cut it off now. I have like 2 slides left. How many slides do I have left? 2? That's okay. I'll finish this up on the next section and we'll continue on from there. Any questions I can answer for you before we let you go? All right, fantastic. I guess I will see you guys tomorrow then.